Okay, guys, need to talk to you a little bit about how this week is going to look. The stuff that we're doing right now is definitely pressing you in terms of what you've learned so far in Chapter 16. And what I want to get from you is not a yay or nay vote, but what I want to get from you is feedback about whether I should, on Monday here, whether we should just do Stokes and Divergence theorem kinds of problems and here do a review and do the exam here, or if I should just leave it as is. So, pros and cons, feel free to comment.
I'd rather have a review before the final.
Well, you wouldn't lose that because I would just do it, I would have some sort of office hour Wednesday night beforehand. But it would not be the same as the review that we do in class. There's no question about that. It wouldn't be group work. It would be, if I do a review for the final, it's just me in a room answering questions, probably be a room like this, and it would just be me answering questions that you've encountered in your studying up to that point. So.
And it'll be that way even if it's on Friday or if it's on any other day?
No. If it's on Friday, it'll be in-class group work kinds of stuff. And I will probably still have that session on Wednesday night, regardless of whether we do this. So, anyway. So again, we're not voting here. I'm just trying to get feedback from you guys to decide how I want to do next week, because I'm the decider. No. Go ahead, Tate.
I think it'd be nice to do the Wednesday session after the exam, so it doesn't get kind of confusing working on a cumulative review while we're also studying for the Chapter 16 exam. Does that make sense?
So keep it on Wednesday?
Keep it on Wednesday, yeah.
He means next Wednesday as in like the night before the exam.
Yeah.
Yes. Oh, yeah. The exam is the following Thursday?
Yeah, no, I understand that.
Okay, got it. So, but your vote. We're not voting. You would keep that there. Okay. Go ahead, Anna.
Some people have really crazy weeks next week.
Yeah.
Having it on Friday would be really
I'm more looking for like pedagogical reasons within this class versus outside, although I will take that into account. Give me an example of how people have crazy weeks next week.
like a last minute midterm kind of thing.
Okay.
I have to take home on Monday and a test Tuesday.
Okay.
I actually love sports too.
Is this unusual or is this like a typical week?
It was everything that was.
Chloe.
I feel like another day spent on Divergence and Stokes.
That's what I'm struggling with. Okay, is that very issue. We would still kind of have that here, and I guess the question is that enough, or do you need two of these? That's yeah. So your vote is yes. I want two of them.
So next Monday we're doing a review for the test anyway, right?
Yeah. So I would see the final exam here on the 13th.
Yeah.
The night before that, I would just have office hours from like 7 to 9ish probably, and then likely, depending on how many people show up, I'll move it out of my office and down into one of the classrooms. Go ahead, Tate.
Well, if we did extra review on Stokes and Divergence on Monday, would you give us like practice problems or something? Because if you maybe.
Yeah, exactly. I mean, we would do group work on Stokes and Divergence theorem exclusively, and then on Wednesday we would do a broader review of Chapter 16, which would probably still include some Stokes and Divergence theorem.
Maybe over the weekend you could just send us the questions you would have given us on Monday, and we could do those and then discuss them very briefly.
Yeah, it's a possibility. I'll think about that.
I mean, you could do the same thing with the Friday potential review too. Send out a review for all of the chapters.
True.
It should be nice.
Yeah, okay. I will think about that as well. So regardless, today, I'm not going to change any of the due dates. Mostly I just want you to beat your head against it for the weekend, even if you're not fully getting it. And I will let you know sometime over the weekend how I plan to run next week. But none of the due dates are changing. None of the homework problems are changing. Just do the best you can with the time that you have. All right. So today I'd like to answer questions that you might have about Stokes' theorem, and then the divergence theorem actually isn't going to take a whole lot of time. The divergence theorem, thankfully, is much easier to visualize and understand conceptually than Stokes' theorem. And I think I can probably knock that out in 25 minutes or so. So questions on Stokes' theorem? Go ahead.
Number one of the web work, I just didn't know where to start really.
Okay. It is pretty crazy. I mean, that's one of the things that's really daunting about these problems is they just like dump all this stuff on you. And 90% of the problem is just parsing these statements. So you just have to sort of take it one piece at a time. So you look at this first thing, it's a capped cylindrical surface, the union of two surfaces. So you know immediately now that they're going to describe two surfaces to you. It's a capped cylindrical surface, so that should evoke, and you've seen this before, you've got a cylinder and you've got some kind of spherical cap on top of it. So let's see what those two pieces look like. The cylinder is a cylinder of radius 7 centered at the origin, opening up along the z-axis. Your numbers may vary, but that's generally speaking what we have. This is a short, fat cylinder. Right? It's 7 units in radius and only 1 unit high. Where is the base of the cylinder? It's lying in the xy plane. And then the top of the cylinder is at z equals 1. That's what this means. So this is the general cylinder. If we didn't have this limitation, this cylinder would extend to infinity in both directions, the z direction, positive z and negative z directions. But we have this limitation. So that means we have this short, fat little cylinder sitting there on the xy plane. Okay, now we have a hemispherical cap. This is a sphere of radius 7 centered where? 0, 0, 1. That's not an accident, because that puts the equator of the upper hemisphere, and notice this is z greater than 1, right? So that's an indication that this is the upper hemisphere of a sphere of radius 7 centered at 0, 0, 1. It's not an accident that this thing is centered at 0, 0, 1 because it puts the equator where relative to the cylinder? The top edge of the cylinder and the equator of this hemisphere are the same, right? They coincide. I like this problem because I call this a Franken surface, because you can glue together different pieces different kinds of surfaces, and what you get relative to Stokes' theorem, where is the boundary of this surface in the context of Stokes' theorem? It's that circular base of the cylinder, right? So this is that's the curve for Stokes' theorem. And how do we want to orient this thing? How do we want to go around this curve? Say, looking down from above. Two choices. Counterclockwise. Looking down from above, we want to do this counterclockwise. Why is that? Because these normals are all pointing upward. Like that. Right-hand rule. Like I said, that's like 80% of the battle, 90% of the battle. They say, compute this thing in any way you like. How would you like to do it? You have two choices, right? You have the double integral, which is sitting right there in front of you, or you can apply Stokes' theorem and reduce it to a contour integral, a line integral. Which is better?
The line integral.
The line integral is better. Why?
We want the z's and things.
There are a couple of nice reasons. One is that contour sits in the xy plane. So what's z on the contour? Z is 0. So that means this guy's 0, that guy's 0, that's 0, and that's 0. That's really nice. Why else would I rather do the contour integral than this surface integral?
So
Eh.
crossing f.
If I do this guy, I've got to find the normal vector, right? And the normal vector is actually of two parts. There's the normal vector to the cylinder part, and then there's the normal vector to the spherical cap. So I'm actually, if I insist on doing this as a surface integral, I've got to break it up into two integrals. The surface integral that corresponds to the sides of the cylinder, and the surface integral that corresponds to the spherical cap. I do those two surface integrals, I add them together, and that's the surface integral. That sounds like a lot of work. It's doable, but I think it's a lot of work. Here, by converting to a line integral, I only have to do one integral, and it's a very straightforward integral. All right. So we all agree that we should use this guy. So now let's parameterize C. And I think my problem had radius 7. I've forgotten already. Okay. So that's a parameterization of the C for Stokes' theorem, and T is between 0 and 2 pi. Is everybody with me so far? And now you have a straightforward line integral that you know how to do from section 2. Okay? This is something, frankly, this is something that I think requires more practice and more drill than understanding Stokes' theorem. What do I mean? I mean parsing these long sentences of mathematical jargon that describe the surfaces or describe the curves, right? This happens over and over and over again. You're presented with this long chain of stuff that you have to parse in order to understand the geometry. You have to get good at that. The only way to get good at it is to do a lot of problems. Go ahead, Joe.
I'm still a little confused on how you decided to parameterize the bottom of the thing. Why is it that part in particular?
So do you agree that the bottom curve is the bottom of this cylinder?
Yeah.
Okay, so this cylinder is x squared plus y squared equals 49. As it sits in the xy plane, right, it's a circle of radius 7. And you simply have to know by this point in the semester that to parameterize a circle, you should pull out sine and cosine.
I know that.
Okay.
Why like, given like a different shape of the cap, why is it always just the bottom part? Or?
That's the boundary, right? This is open under here. Right? That's the only place that it's open. And essentially what you want is the curve around the opening.
Oh, okay.
That's a little, you know, you don't always have an opening. For example, some of your problems look like this. And now the surface is a plane, and the Stokes curve is the boundary of the plane. That's not really an opening, per se. It's just the boundary. But in this case, it literally is the opening of the surface. Go ahead, Logan.
I guess I'm confused. Once you get that, then you dot it with f? Is that what we're doing?
Once I get...
To the 7 cosine t, 7 sine t, 0? Or is
No, now you're back in section 6.2, so now you do r prime. And then you also have to do f. Right? Remember what f was. So I have to plug in 0, 0, z is 0 here, z is 0 here. I have what, 35 sine t, 0, 9 times 7, 63 cosine t, and 0. And then dot that with r prime, and then integrate it. Okay.
Wait, why are you plugging in this?
I'm plugging in the parameterization. So the parameterization, this is x, this is y, this is z. I take that and I dump it into f. So everywhere I see an x, it's a 7 cosine theta. Everywhere I see a y, it's a 7 sine theta. Everywhere I see a z, it's a 0. And you can see that that z equals 0 is helping me quite a lot. Here, 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 and here.
For the r, what the z coordinate was 0.
Yep.
Why is it 0?
It's the bottom of the cylinder, not the top. And the bottom of the cylinder lies in the xy plane, where z is 0. So I'm simply parameterizing the bottom of that cylinder.
Would it be the same if you didn't do top?
It wouldn't be, because that top curve occupies a different part of the vector field. So it's really important that you get the opening of the surface down there. I wish I could give you a better way of visualizing Stokes' theorem and why it works, but it's really hard to visualize for these kinds of situations. So you just kind of have to take my word for it.
I think on question 3 or 4, it's kind of similar to this. It has a cylinder with an open top, I think. Maybe 4.
Oh, it's 5. That's the cylinder with the open
Yeah.
top. It's 10 to 5.
That one.
Yeah.
So in that case, would you make z equal to whatever its top coordinate would be?
Yeah, in fact, they actually sort of indicate here with this black line what the curve is. And I guess one question is, why is this thing parameterized clockwise instead of counterclockwise? It's this sentence right here. If S is oriented outward and downward, if it's down, you have to parameterize it the other way. But it's exactly the same situation. Yeah, that's the opening of the surface, and you want the boundary of the opening loosely defined. Other questions?
I think it might have been number 3. You said measurement? I'm not sure. It might have been 3. No, I think 2. Yeah, so I got N and I got the curl, but for some reason I couldn't get I don't think I was using the right limits of integration, maybe?
Yeah, let's look at these 3 points. So we have 1, 0, 1, 0, 1, 0, 0, 0, 1. And I think the best way to figure this out is to look down from above. So I'm looking down now on the XY plane. And so I'm looking down from above. This is 0, 0, 1. So it's up here somewhere. This is 1, 0, 1. So it's up here. And this is 0, 1, 0 down here. So it looks like that, kind of, right? It's this plane that comes up.
Okay, I was just looking at it wrong.
And now if you project that down into the XY plane, this will tell you what the limits of integration should be. So if you do Cartesian, which I think you should do, in this case, y would go from 0 to 1 minus x, I guess, and x would go from 0 to 1. So those will be the limits of integration in that problem. Other questions?
How do you find N for that problem?
Well, you've got this, there's this plane that goes through these 3 points, right? Actually, there's not a plane. This is a good question. Use Stokes' theorem to evaluate the integral of f around the curve consisting of these 3 straight lines. So the Stokes curve, the Stokes boundary curve, is this triangular piece of thing, and it's just sort of sitting up here in space, right? If you were to not use Stokes' theorem, you would have to do 3 integrals, this guy, and this guy, and add them together, and that would be a pain. So you're allowed to use Stokes' theorem, in other words, turn that line integral into an area integral. The question is, what's the surface that I'm using? Well, what surface am I allowed to use for Stokes' theorem in this context? I can use any surface that has this as its boundary. What's the simplest surface that has this as its boundary? The plane. The plane through these 3 points. Right? I could take some crazy hot air balloon that has a weird triangular opening and it could like be all over the place. But the simplest surface to use is the plane that goes through these 3 vertices. How do you find the equation of that plane? Do you know how to do that? Find the equation of a plane through 3 points? You find the 2 displacement vectors, you do the cross product that gets you the normal vector, etc., etc. So what you have to do is decide which surface you want to use for Stokes' theorem, and the best decision is the plane. I can't even think of another surface that would be easy to use in this context. Use the plane that goes through those 3 points, and then proceed from there. Other questions? Yeah.
Could you show us how to parameterize F for number 5?
Sure. So we have this cylindrical can, and it's standing on the xy plane, and its height is 5. So the top edge there is sitting at z equals 5, right? Yes? Okay. I know how to parameterize a circle. I always start in the with a circle in the xy plane centered at the origin, and then I just make tweaks to get me to where I want to go. So start with a circle in the xy plane. All right. Well, I know how to parameterize that. Like that. And if I want to make it have a radius, for example, I don't remember what the radius is here. Oops. The radius here is 4, at least for in my case. So I'll tweak it. Now, this guy is going, which way is this parameterization oriented? Counter. Right, it's just the traditional way of parameterizing a circle, which is the wrong direction, right? How can we turn it around? Sorry? Actually, that won't get it for me. You could do that. I don't know if you can do that either. Let me show you the easy way. Just do r of minus t. And you know that cosine is an even function. So the cosine of minus t is just the cosine of t. And sine is an odd function, so the sine of t is, sine of negative t is just minus the sine of t. So we're almost there. This is now parameterized in the correct orientation. The last thing I need to do is get this thing out of the xy plane and up to z equals 5. How do I accomplish that? Sorry? Change the 0 to 5? Yeah. So the final parameterization here of that curve is given like that. Does that answer your question, Anna?
Yeah, I think so. I tried this a couple times and all my answers were so.
Is this the parameterization that you used?
No.
Well, try that and see if, and if you're still stuck, come find me. Logan.
And does t, how do we know what t goes from?
T is 0 to 2 pi here, yeah. And let me just try to motivate that t to minus t thing. Right, so in the traditional parameterization, t started out here and it kind of went this way, right? Now, if I change t to minus t, it still starts out here at 0, but where does it go? It kind of heads off in this direction, right? And that gives me that's what gives me the opposite orientation. This doesn't always work, but it works for intervals that start at 0. If you have an interval that starts at 0 and goes out, you can just change the sign, and that'll give it the opposite parameterization. Okay, other questions? Really? Go ahead, Stuart.
So what happens when it's not at the origin? How do you parameterize that?
Yeah, that's a good question. So there was a problem, I believe, in the web work that dealt with that as well. Number 3. So here you're asked to find the circulation of F around the circle C, and this circle is annoyingly placed well away from the origin. Okay, you're asked to use Stokes' theorem, which means given a line integral, you have to go to the area integral. Now, to go to the surface integral, you're allowed to use any surface you want that has this circle as its boundary. What's the easiest surface to use? The plane that goes through that circle, right? The plane that contains that circle is the easiest one. So now what you're left with is, how do I parameterize that circle, the disk that went from the origin and is now sitting up here at, in my case, 9, 5, 6. How do I deal with that? I do the same thing. I sort of build it up from first principles. So how do I parameterize the surface if it's down here? If it's down there, then I do I do u cosine v, u sine v, and 0. And the parameter ranges are going to be 0 less than or equal to u less than or equal to, say, 1, and 0 less than or equal to v less than or equal to 2 pi. Does everybody see why that's the case? How if I let u and v range over these intervals, I'm going to fill out this whole circle. Not just the boundary, but in fact everything inside. Right? One way to see that is, if u is equal to 1, what part of this set am I accounting for? The outside, right? The boundary. Let's fix v. If v is equal to, say, pi over 2, what part of the set am I accounting for? The line from the center of the circle up to all the points along here, right? So you can see that a combination of u and v allowed to vary over those intervals is actually going to account for every point inside there. So I have parameterized this little piece of surface that lies inside this circle of radius 1 at the origin. How do I know that this is a circle of radius 1? What determines that? The parameter range. In particular, this guy right here is what determines. Okay, how do I get that circle out to where I want it and to have the size that I want? I don't even remember what the size I wanted was. So the radius is 3. and I want this thing up at 956. So let's get the radius equal to 3 first. What do I have to do?
Change the 1 to a 3.
Exactly. So I'll just change that to a 3. And now I've got radius equal 3. Now, I want this guy not sitting centered at the origin in the xy plane, but I want it up here at 956. How do I do that? It's actually much easier than you might suspect. Joe?
You do 9 minus u for u cosine b, and then,
Not minus.
what?
Yeah, I take a point here, and to get it in the right place, I add 6 to its x coordinates, I add 5 to its y coordinate, and what was it? 9, 5 something, I don't remember. 6. So 9, 5, 6, and it gets it to the right place. And I just always want to do that. I want to add 9, 5, 6, and that's going to move the thing to the right place. So all I have to do is plus 9, plus 5, plus 6 in each coordinate. And there's a parameterization of that little piece of surface. I suspect now maybe once you have that parameterization you can do the surface integral. Okay. Stuart, yes? Okay. Any other questions? Okay, let's do the divergence theorem and get you guys on your way. So of all of the big 3 theorems, if I had to rank them in mathematical importance, I would put the divergence theorem at the top. And then the next big theorem, the Green's theorem, I would put second, and then Stokes' theorem comes in third. Not because Stokes' theorem is not a great result, but it's just not widely used in physical situations, whereas the divergence theorem and Green's theorem are often used in physical situations. The divergence theorem goes like this. Let me set it up a little bit first. If V, I think we use E in the book. If E is some bounded volume of space, and the boundary of E, the partial V, is the outward oriented boundary of E, then we have the following result. The integral around the boundary, the surface integral around the boundary of f dot n ds is equal to the integral over the interior of the divergence of f dv. Thankfully, this one has a really nice interpretation to it. Let's pretend we have some body. This is E, and the boundary of E, and it's got all these normal vectors all over it. And it's sitting inside a vector field. This guy here, you know what this is already. This is a flux integral, right? This is the flux of f across the boundary of this thing. And what all this thing is saying is that the flux across the boundary is the same as what you would get by adding up the divergence everywhere throughout the body. This is really just a generalization of Green's theorem. You'll remember you'll remember Green's theorem goes like this. The integral around the boundary of some shape D, say, of f dot n ds is equal to, trying to remember here, did we just do the divergence? I think we did just do the divergence. So it looks exactly the same, except we've added an integral sign to each side. We've lifted the whole thing up one dimension. And you'll remember the picture that I painted for you of Green's theorem, where we had a plane curve and we looked at a little point and we looked at how stuff was flowing away from that, and we looked at a guy right next to it and we looked at how stuff was flowing away from that. And what we noticed was that in between the 2 points, the stuff flowing out of one point was immediately canceled by the stuff flowing out of the other point. In other words, there was lots of cancellation in between, in the middle, but there failed to be cancellation around the boundary. So you have a guy out here, say, and there's stuff flowing out here, and there's stuff getting canceled in here, but there's nothing to cancel out here. And so the contribution of divergence from this point actually doesn't get canceled out. So all the stuff inside gets canceled out, but not this guy. That picture actually lifts right up into higher dimension. Okay, the divergence inside this body, they all kind of cancel each other out except for the ones out on the boundary. Chloe?
So for the divergence theorem, it's f dot n ds. Would that be the non-voltage ds?
Yes. Other questions? So this is a generalization of Green's theorem, and frankly, when I ranked divergence theorem and Green's theorem, 1 and 2, you could sort of mush them together and really just call them one result. Okay, let's do an example here to see how this works. You'll be happy to know that the divergence theorem rarely goes the other way. You rarely are presented a problem. You almost always want to do the volume integral, is what I'm saying. You rarely want to, if you have to choose one or the other, it's very rare that you want to choose the surface integral. Almost always you want to choose the volume integral. Whereas the Stokes theorem, right, it was sort of a coin toss. Sometimes you did the contour integral and that was easy, or sometimes you did the surface integral and that was easy. Okay, let's look at an example here. Let's let E be the sphere of radius A, centered at the origin. And let D be the surface of E. Let's let F be a very simple vector field, 0, 0, Z. And let's compute this surface integral, the integral over D F dot N ds. So this is the flux of this vector field across the surface of the sphere. Let me draw you a picture. Here's a sphere. There's the z-axis. Describe for me this vector field. Jefferson. What direction does it have? Is it always up?
No, when it goes, like when it's at 0 and then afterwards down.
So if I'm at points above the xy plane, this guy points up, and if I'm at points below the xy plane, it points down. Everybody see that? What about the magnitudes of these vectors? What happens to them? The further away I get from the xy plane, the larger the magnitude. Does everybody see that? So if I'm at the same height above the xy plane, these vectors all have the same length, and they all have the same direction. And let's put the plane in there. And if I'm below, they all look like this. Guess. Flux. Positive, negative. Not zero. Why positive? The normal vector for the sphere. In the northern hemisphere, the normal vector has a slight upward tilt, right? And so the dot product of this guy with one of these guys, the angle between them is acute, right? Which means it's going to be positive. So if we look at that flux integral across the northern hemisphere, we expect a positive number, because the normal vector points in roughly the same direction as the force field. Does everybody see that? Let's look at the southern hemisphere. Down in the southern hemisphere, all the normal vectors have a slight downward tilt. So too, the vectors of the force field. They all point down. So the angle between them, again, is acute. So the flux integral across the lower hemisphere is also positive. Add those two guys together, you get a positive number. So we expect a positive number out of this calculation, this flux integral, right? Now, I don't want to do the surface integral. I want to see if I can use this new tool that I've just shown you, the divergence theorem. The divergence theorem says that I can either evaluate the surface integral over D, or I can evaluate the divergence of F over the volume. What's the divergence of F here? The divergence of F is the partial of partial with respect to x, partial with respect to y, partial with respect to z, dotted with 0, 0, z. What comes out of that calculation? 1. The constant 1. So the integrand of this volume integral is what? 1. And the volume integral itself is what? It's the volume of the sphere, right? Which is 4/3 pi r, oops, not r, a, thank you. 4/3 pi a cubed, positive number. Also, just as a side note, this is a way of calculating the volume of any figure E, right? There was nothing special about the sphere in this particular problem, was there? It could have been any volume, any closed volume. If I do the flux integral, I get the volume of the body. This is similar to way back in Green's theorem where we had those formulas. Remember, if P was, what, minus y over 2 and Q was x over 2, and you did the Green's theorem to it, you would get the area of the enclosed volume. You remember that? It's very similar. Let's do a slightly more involved version, or a slightly more involved example. So let's let E be the solid bounded above by the hemisphere. Let's see, Z equals A squared minus X squared minus Y squared 1/2. And below, by Z equals 0. So let's let D be the boundary of this figure and evaluate the flux. F dot NDS. Let me be very clear about how this theorem works. This theorem only works on closed and bounded volumes. Why is that? Because only closed and bounded volumes have nice surfaces. Unbounded. Let's think about unbounded for a second. Suppose I take the collection of points in three-dimensional space, x squared plus y squared less than or equal to 1. What does that collection of points look like? X squared plus y squared less than or equal to 1 in three-dimensional space. In two-dimensional space, it's the inside of the unit circle, right? But in three-dimensional space, it's a cylinder, right? It's a solid cylinder. And how far does that cylinder go? As far north and as far south, as far up the z-axis and as far down the z-axis as you want to go, right? What's the boundary of that surface? Sorry, the boundary of that volume. What's the boundary of that volume? No, it's actually not that. I'm on a tangent. So I have this solid cylinder all the way up, all the way down. What's the boundary of the solid? It's just the surface of the cylinder, eh? Like x squared plus y squared equals 1? Yeah? Okay. We can't do the divergence theorem on that guy because it's unbounded and the surface of the solid is unbounded and it's not even closed. So we're only going to consider things like this. This guy is the upper hemisphere, right? Upper hemisphere. And it's bounded below by z equals 0. And it's all the stuff inside. So the boundary of this thing is actually two pieces. It's that upper hemispherical shell and that circular disc on the bottom. So doing that surface integral will be a pain in the butt. Why? I'd have to do two integrals. I'd have to do the one for the bottom and the one for the sphere. I can avoid that misery by using the divergence theorem. Okay, well, let's do the divergence of f. Gosh, I don't know if I ever wrote down f for you, did I? Alas. F is barely important in these problems. X cubed, y cubed, z cubed was f. So the divergence of f is just, 3 times x squared, y squared, z squared, oops, plus. So there's the divergence of f. So this integral, this triple integral becomes how do you suggest we do this integral?
Spherical.
Please, yes, spherical. Okay, the integrand becomes what?
Rho squared sine.
Well, the integrand, yeah, okay. So this guy becomes 3 rho squared, and then you also have rho squared sine phi d rho d phi d theta, right? Where's this guy come from? That's the Jacobian of the spherical transformation, right? And this piece here came from this. Does everybody see that? Limits of integration. What does rho do? Goes from where to where? 0 to a, good. Phi, be careful.
0 to pi.
Since it's the upper hemisphere, 0 to pi over 2, and theta is friendly old 0 to 2 pi. You can do that guy and you'll get 6 pi a to the 5th over 5. The reason that we talk about one of the big physical applications of the divergence theorem, although I cannot overemphasize how important a theoretical result this is in higher mathematics. You use this theoretical result in proving higher level mathematical theorems quite often. But one of the reasons that we teach it to you at such an early point in your college careers is, especially if you're going to do physics or engineering or something along those lines, is this has implications in particular in electricity and magnetism. If you, for example, does anybody know Gauss's law? From E&M? Do you, or not really? No.
Yeah.
Okay, I'm not going to put you on the spot. You've heard of it before. Other people have heard of it? Ish? Heard of it? Okay, Gauss's law. I know. Gauss's law says that the flux of the electric field across a surface is equal to the amount of charge inside the surface. So if you can somehow figure out what the flux is across a particular surface, you can figure out how much charge is inside. That may sound like a really hard problem, but remember, like if you have a point charge, if you have some charge sitting here in space, if I can measure the electric field here, it's not hard to figure out what the flux is across the whole sphere. And so in fact, I can figure out how much charge is sitting right there, just from one measurement. So this is a really important result. And it has generalizations that go far beyond that simple example that I just described. Let me show you how this relates to the divergence theorem. We know that the electric field is often denoted E is just some vector field. How does that work? Well, I've got this charged particle sitting here and I take a point in space. The electric field is a vector that tells you the magnitude and the direction of the electric field at any particular point in space. So it is a vector field. What you have is you can do the flux across some surface, D, say, So the flux of the field across some surface is the integral, is that just that flux integral that you're already familiar with. And then the thing that you may not know is that charge density is given by sigma, the divergence of E. So the charge density in a particular volume of space is actually just the divergence of the electric field. Now, Gauss, the divergence theorem says that this is equal to the integral over the volume dV. So if you know that this is charge density, density times a little piece of volume is what? Charge density times a little piece of volume is charge. Sum up all the charges inside, and you're done. So the flux is equal to the charge inside. I don't know, frankly, I don't know my math history well enough to know what came first. Whether Gauss discovered did the physical observation first, and then the math came along later, or whether the math came along and then that led to the physical observation. But you see this often, there's an interplay between math and physics. Physicists will discover something, and then the mathematicians sort of scramble and try to make sense of it using logic and mathematics. And then you also see the reverse. You'll see mathematicians run off and do something, and then the physicists will be coming along and studying the universe, and they'll grab pieces of this abstract mathematics that actually happens to be relevant. Let's see. I can probably come up with examples of both directions. In the 1800s, people started studying non-Euclidean geometry. This is geometry on non-flat surfaces, non-flat universes. And then in the early 1900s, a guy by the name of Einstein came along and used that non-Euclidean geometry to formulate his theory of general relativity, which relies on the fact that three-dimensional space is not actually as flat as it looks. It's actually curved. And one of the demonstrations of that curviness is the fact that light bends around stars and bends around massive objects. Maybe you've heard of that, maybe you haven't. But light, that you can see the curviness of space by looking at how light bends around massive objects, and that's a confirmation of general relativity. The other direction, so that's math leading physics, physics leading math. How many of you guys have heard of the Dirac delta function? Any of you guys? Okay, so you run into that. Where did you run into it, Jefferson? Do you remember? In quantum? Yeah, that's the standard place. The Dirac delta function was something that quantum physicists started using in the early part of the 20th century. And it made no mathematical sense whatsoever in the context of the time. It had no mathematical foundation. The reason the quantum physicists used it is because it made sense and it worked. Sorry, it didn't make sense, but it worked in their calculations. And so it left the mathematicians in a bit of a quandary. Why does this thing work? And the long history of cooperation between mathematics and physics suggests that there's something deeper going on with this Dirac delta function. And so they scrambled and they come up with a whole new area of mathematics, really, the area of functional analysis, Hilbert spaces, Banach spaces, all that stuff came out of essentially cleaning up the mess that the quantum mechanics people made when they laid out quantum mechanics. They laid it all out and they didn't care about the math, and then the mathematicians came along and swept up behind them and cleaned up the theoretical mess that they had created. Let's talk about a couple other consequences here and then I'll let you go. What if F is incompressible? what does it mean for F to be incompressible? Do you remember?
Now the dot F is
The divergence is 0. Okay, what are the implications of this in the context of the divergence theorem? Well, let's look at that. The boundary d f dot n ds equals the integral over e of the divergence of f dv. So if f is incompressible, what happens to this equation? The right-hand side is 0. How do you interpret that for the left-hand side? What is the left-hand side? It's a flux integral, right? So how do you interpret that? This is saying that the flux is 0.
Vector fields perpendicular to this.
Does that make sense? Flux is 0? It's incompressible. What I want you to do is I want you to think about a floating blob of water right here. Water's incompressible, right? And suppose it's sort of trapped inside an imaginary sphere. Now suppose I take this little blob of water and I push it in here. What's going to happen? Somewhere something's got to pop out because it's incompressible, right? So I take this little blob of water and I shove it into the sphere. Somewhere somebody's got to leave. Now when I push that thing into the surface, that's negative flux, right? When that guy pops out, what's that? That's positive flux. When I add those fluxes together, they cancel. And that's true of all incompressible vector fields. If I push something in one side, it's got to pop out the other side, and that means the flux balances over a closed surface. I love the divergence theorem because it has all these nice interpretations. Any questions about that? Let me close with just a quick review of the web work. Okay, you're going to see, I haven't had a chance to do a lot of examples for you, but evaluate this. This is a flux integral, right? That's a bold S, so hiding in there is an N. So that's a flux integral, where F is given by that, and W is the solid rectangular box whose sides are bounded by the coordinate planes and the planes blah, blah, blah. Okay. This is a box. You don't want to do a surface integral over a box. Why? Because there's 6 integrals I got to do. So by all means, take the divergence of this thing and integrate over do the triple integral over the box, because triple integrals over boxes are really easy, right? It's going to be like 0 to 6, 0 to 5, 0 to 8, and you're done. And you're going to see a lot of boxes in this exercise, because that's really how you end up using this. You take surfaces that are really a pain in the butt to work with, and suddenly you turn them into volume integrals, and all your pain goes away. Here's the outward flux across the surface of the region that's enclosed by the cylinder of radius 2, and then it's got a top at z equals 5 and a bottom at z equals 0. Take the divergence and integrate it over the volume. Probably going to use polar coordinates in this one, right? Maybe. Here's some nice true or false statements. I'll let you chew on those. Rectangular prism, don't be fooled by the terminology, it's just a box. This is a little more complicated. I would suggest in this problem that you use spherical coordinates. But again, you've got this nice long list of conditions, and I want you to think about how to parse that. Another box. And, oh, come on.
There is no one.
Oh, awesome. Have a good weekend. Go to basketball tonight. Yay, basketball.
Why do we need to tack on the Jacobians when we're doing...
Spherical coordinates?
Yeah, why is it always going to be spherical? I've forgotten why we have to tack on the Jacobian.
Well, I mean,
I don't know if there's a quick explanation or not.
there's kind of a quick explanation.
Because I looked through my Jacobian notes.
So David tries to explain it right here about where that comes from. Okay, about where rho squared sine phi comes from, I mean. And then you get a much better, in my opinion, you get a much better explanation down here when you look at it from the context of change of variables. And somewhere down here.
So when we do spherical, and always we're supposed to tack on the rho cosine?
When you change variables, so when you have a Cartesian integral and you change it to spherical, you have to introduce rho squared sine phi as well.
Okay, I think I just forgot that.
Okay.
Gotcha.
Is it called Clayton Collins? Yeah. Go ahead.
Can I ask a really quick question about the star problem?
Sure.
For 16.7? It's number 10. Sorry.
That's okay. Number 10, you say?
Yeah.
Go ahead.
So then is this kind of the right shape? Like kind of like a weird kind of almost cone over a flat disc?
Yes.
And so then you just have to do two surface integrals. One is the funky cone and the other disc.
It's kind of like that. So z equals x squared plus y squared is a parabola that opens up like that, right?
Yeah.
Now, when you change its sign, so minus x squared minus y squared, it flips over. So now you're like this. Then when you add a squared to it, it moves it up a squared. And now you want it to be between, you want to only consider the part of the surface, the xy values, that are less than b squared. So this guy, your picture's almost right, so that's right. Do you have a pen?
Yeah.
Here we go. Is that, I think I wrecked it.
No, it's fine.
Okay.
Yeah.
Okay.
Sorry.
It's okay. So this guy actually keeps going down and keeps getting wider and wider as it goes down. And so what you do is you project this down and it hits. And that's the part of the surface. It's where this guy projects down and hits this, so it's all of this stuff. But that's actually not going to complicate your life at all, really. But I want you to think about that. The limits of integration are defined by this region in the xy plane.
Okay. So it's this, like...
Oh, and I don't know what A is. Is A...
It's just...
It doesn't say whether A is bigger than B or less than B. If A is bigger than B, then you have sort of a different picture. Yes, it is.
I'm sorry.
Got quite a line going here. So if A is bigger than B, then it stretches out like this, and then the projection goes up. But again, it's not something that you have to worry about. That circle, that B circle, defines the limits of integration when you finally get down to it. So think about that. You were next, Clayton?
Yeah, all I was going to ask is that I haven't had enough time to work on the web work, and I won't tonight. So is there any way I could get it extended? I mean,
yeah, send me an email.
Okay.
Jade.
I had a question about the same problems I asked you about yesterday. It was the ones where the circles were off center. The web work.
Okay.
I also tried it.
I'm gonna turn on the light.
Okay. I also tried it, I used the parameterizations you gave me, and then I also looked at the way I tried it before, which is where I just used like the plane, and then when I integrated it like over the circle or the sphere, then I still got the same answer.
Yeah, that's because this is a constant vector field.
Okay.
And so it doesn't really matter where it is.
Okay. But that wouldn't work on
that wouldn't work if it was a variable vector field. Then you really have to be careful. So what you did was you parameterized a disk that was exactly the same size, and then you didn't put it in the right place, but it didn't matter because the field's the same here as it is over here.
Okay.
Okay.
And then my other question was, are divergence and flux synonyms?
No.
No? Divergence is like...
Although the divergence theorem kind of relates the two, but they are different things.
Okay. And because divergence is like measuring
how much, like at a particular point, how much the fluid is kind of spreading apart or coming together. And flux is measuring how much of the field is crossing the boundary.
Okay.
They're related, as you can see, but they're not the same.
Okay. Okay. Thank you.
Oh, yeah. Do you have something to write with?
That's not a pen, is it?
Exactly. You guys have a quick question?
Oh, we have a gift for you.
See here. First major, second major, that's me.
Yep.
Always second on these things. Kills me. Welcome aboard.
Sweet.
You can meet with either one of us. You don't have to meet with both of us. And if you have questions about math, you come see me.
Yeah, I think at some point I want to ask you a question about math and like the statistics class I take.
Okay.
But
you've got time.
Sounds
okay.
Good. Okay. Thank you.
See you later, Scott.
Yeah. Have a good weekend.
Yeah. What's up, guys? Ooh.
So
I always like paraphernalia.
And you come to all of our games, so
nice.
Enjoy. Grab them. It's from Haley too, but she's.
Is Haley okay?
Yeah,
Okay.
Yeah, she's okay. She's
all right. Well, sorry about Eastern.
Beginning of my work.
But yeah, those are my drawings. Yeah.
Lecture notes.
Yes. So I could use that. But that's not right. So you need to use
I don't know how to sound. Purposely for smart.
is so you do. Is that
Just enough, like 3 pages.